In today's session, we are going to derive Michaelis-Menten equation. But before that, let us understand what are enzymes and how enzyme kinetics are applied to derive this Michaelis-Menten equation. These are the characteristics of enzymes. Enzymes are biological catalysts. Enzymes accelerate chemical reaction by lowering the free energy of activation without being changed itself. They are as potent at the end of the reaction as at the beginning. They are necessary as most biological reactions are very slow. Hence, very small amount of enzyme concentration can affect the conversion of large quantity of material. Hence, they are really a true catalyst. Now, let us concentrate on enzyme kinetics. Kinetics is the study of reaction rates, and study of enzyme kinetics is important to reveal the catalytic mechanism of particular enzymes. When an enzyme added to a substrate, reaction occurs in three stages. First, pre-steady state, second, steady state, that is equilibrium state, and third, post-steady state. Now, to understand this, we must know the, the basic difference between the kinetics of non-enzyme catalyzed reaction and enzyme catalyzed reaction. Now consider a simple non-enzyme catalyzed reaction where a single substrate is converted into product. We analyze the kinetics of this reaction by measuring the rate of formation of product over time, which is expressed as per the rate equation. Now, minus ds upon dt is equal to K into S, where S is the substrate concentration, minus ds upon dt is rate at which the concentration of substrate decreases, and K is rate constant. This can be expressed as minus ds upon dt is equal to V, where V is the velocity or rate of reaction. In kinetic experiment, we examine the concentration of product formed per unit time, which is known as rate of the reaction or velocity of the reaction. We can determine the rate constant by measuring the formation of product over time for different concentration of substrate. Now here, in this chemical reaction, where single substrate is converted into product, as the substrate concentration increases, initial rate of reaction, which is also termed as V0, is exactly proportional to the concentration of single substrate. Hence, we get a linear correlation between V0 and substrate concentration. This is known as first order kinetic reaction. So let us see kinetics of enzyme catalyzed reaction. Enzyme kinetics could be defined as the quantification of an enzyme activity in terms of the rate of conversion of substrate into product based on time or enzyme concentration. Simple enzymatic reaction happens in two steps. First, the association of enzyme and substrate to enzyme substrate complex, and then conversion of enzyme substrate to product, which is then released. Here in this reaction, enzyme reacts with the substrate, gives enzyme substrate complex, and then enzyme substrate complex dissociate into free enzyme and product is released. This reaction occurs in three stages with distinct kinetics, as I said earlier: pre-steady state, steady state, and post-steady state. So let us see these stages one by one. In this reaction, the first step is reversible with rate constant K1 for forward reaction and K minus 1 for reverse reaction. And the second step is irreversible with rate constant K2 for forward reaction because the rate of formation of enzyme substrate from E plus P is very small and may be neglected. So K minus 2 is very small and negligible. Now let us see the first step of reaction. Enzymes are globular proteins. They have an active site which is made up of amino acid and is almost complementary to the substrate shape. Therefore, when substrate binds, the enzyme changes its shape slightly to fit into it. This forms the enzyme substrate complex. Now let us see the effect of this substrate concentration on rate of enzyme catalyzed reaction. Now, in this graph, you can see here that at low substrate concentration, the initial reaction velocity is V0 is proportional to the substrate concentration, and the reaction is in first order with respect to substrate concentration. This first step is very fast and is known as pre-steady state, where rate of formation of product is slow at first and then speeds up as enzyme substrate complex forms. However, as the substrate concentration increases, there is less increase in initial rate of reaction, and now it is no longer proportional to the substrate concentration. In this zone, the reaction is mixed order. When there is further increase in substrate concentration, the rate becomes constant and independent of substrate concentration. In this range of substrate concentration, the reaction is zero order, and this state is known as steady state, where enzyme substrate complex formation remains constant and the rate of formation of product is also constant, but faster than pre-steady state. In this state, enzyme is spoken of as being saturated with its substrate. All enzymes show saturation effect, which is a peculiar feature of enzyme catalyzed reaction, and we get maximum rate of reaction, which is called Vmax. The last step, that is dissociation of enzyme substrate into free enzyme and product, is the rate limiting step, and rate of product formation is very slow as there are fewer enzyme substrate complexes formed because substrate concentration decreases. This stage is called post steady state. For all enzymes that obey the Michaelis-Menten kinetics, a graph of initial velocity V0 versus substrate concentration gives a rectangular hyperbola. So with this knowledge of enzyme kinetics, now let us move on to derivation of Michaelis-Menten equation. In 1913, a general theory of enzyme action and kinetics was developed by L. Michaelis and M. L. Menten. Michaelis-Menten equation is a rate equation for reaction catalyzed by enzymes having a single substrate, and it expresses the mathematical relationship between V0, Vmax and substrate concentration. In this derivation, we are going to use the following terms. Concentration of free enzyme or uncombined enzyme. Es represents concentration of enzyme substrate complex. E minus Es represents concentration of free enzyme or uncombined enzyme, and S represents concentration of substrate. To define a general expression for V0, the initial velocity of an enzyme catalyzed reaction, assuming that enzyme catalyzed reaction takes place in two steps as shown in reaction 1 and reaction 2. Now, the rate of formation of enzyme substrate from E plus S is given by the following equation. Equation number 3. The rate of formation of enzyme substrate from E plus P is very small and may be neglected. Similarly, the rate of breakdown of ES is given by equation number 4. Now, when rate of formation of ES is equal to rate of breakdown, that is, when the reaction system is in a steady state with the enzyme substrate concentration remaining constant, equation 3 and 4 gives us equation number 5. Rearranging this expression, take rate constant on one side and rest of the terms on other side, we get the equation number 6. The constant term is Michaelis-Menten constant. So it is written as Km. From this equation, the steady state concentration of enzyme substrate complex may be obtained by solving for enzyme substrate complex concentration. So from equation 6, we can solve for enzyme substrate concentration, which is given in equation number 7. Since the initial velocity V0 of an enzymatic reaction is proportional to the concentration of enzyme substrate complex, we can write V0 is equal to K2 into enzyme substrate complex concentration, that is equation 8. We can now substitute for the term enzyme substrate concentration in equation number 8. Its value from equation 7. We get the V0, which is given in equation number 9. When the substrate concentration is so high that essentially all the enzyme in the system is present as the enzyme substrate complex, that is, when the enzyme is saturated, we reach maximum initial velocity Vmax is given by Vmax is equal to K2 into enzyme concentration, equation number 10. If we now divide the equation number 9 by equation 10, we get the equation number 11. And then solving for V0, we get V0 is equal to Vmax into substrate concentration upon Km plus substrate concentration, which is known as Michaelis-Menten equation. Thus, Michaelis-Menten equation defines quantitative relationship between the enzyme reaction rate and the substrate concentration if both Vmax and Km are known. But when the initial velocity V0 is exactly half of the maximum velocity, then we get the following equation: V0 is equal to half Vmax. Now substitute the value of V0 from equation 12, we get Vmax upon 2 is equal to Vmax into substrate concentration upon Km plus substrate concentration. Now divide above equation by Vmax on both the sides. Vmax get cancelled and we get 1 upon 2 is equal to substrate concentration upon Km plus substrate concentration. On rearranging the terms in above equation, we get Km plus substrate concentration is equal to 2 into substrate concentration. Therefore, Km is equal to substrate concentration. Thus, Km, that is Michaelis-Menten constant, is equal to the substrate concentration at which the initial reaction rate is half maximum. Now these are the significance of Km and Vmax. Km value is used as a measure of an enzyme's affinity for its substrate. The lower the Km value, the higher the enzyme's affinity for the substrate and vice versa. Km is the concentration of substrate at which half the active sites are filled. It provides a measure of the substrate concentration required for significant catalysis to occur. Whereas Vmax reveals the turnover number of an enzyme. Turnover number is the number of substrate molecules converted into product by an enzyme molecule in a unit time when the enzyme is fully saturated with substrate. That's all for this Michaelis-Menten equation. Thank you.